So my name is Nakong Teddy Computer Science here to Macquarie University, and together with my colleague, we're going to take you through our machine learning project under the topic multi-strategy sparse knowledge distillation for fraudulent gas and power consumption detection. So under our topic, we have some keywords. We have anomaly detection. This is concerned with detecting unusual occurrences in data. Then we have deep learning. Deep learning is concerned with use of neural networks to solve complex tasks. Then fraud detection, for it is concerned with detecting these fraudulent activities that we're talking about. Then with machine learning, for it, it's teaching machines how to do tasks, but not explicitly telling them how to do it. So then with multi-strategy learning, for it, we mean use of multiple strategies or techniques as a training the model to do specific tasks. Then power fraud, for it, consumers deliberately steal this power that you're talking about. Then sparse knowledge distillation, for it, it's concerned with distilling knowledge from the teacher model to the student model. So some of the contents we have in our presentations listed there. We have introduction, related works, problem statements, and research questions and objectives, our contributions, the methodology, dataset descriptions, results, conclusions, and anticipated limitations, and counteraction plans, and then the references. So I'm going to take half of it, and then my friend will take you through the rest of the part. So first, we're talking about fraud in gas and power consumption. This is a concern to really take note of because it causes financial losses and perhaps inaccurate billing. So this leads to losses for these companies that provide these services, the power and gas we're talking about, and also sometimes overbilling to these individuals. So traditional methods, we realize that they really face challenges with scalability and high false positives in the data that they use, even the imbalance of the data. So they also face problems of computational inefficiency. So that necessitates our project. That is where we come in with our multi-strategy sparse knowledge distillation for fraudulent gas and power consumption detection. Our project integrates teacher models of XGBoost, then artificial neural networks and random forests as teacher models, and it also involves a smaller random forest student model that is developed, and it is taught on soft levels of the teacher models after evaluating their performance. So this ensures scalability and efficiency when recording this fraudulent detection, when doing the fraudulent detection. So we were able to work with some related works, and under this table we have some research papers related to what we're looking at. So some of the papers we have fraud detection in electricity consumption, and then we have predictive data analytics for electricity fraud detection, and then we also have machine learning electricity fraud detection. So these with the corresponding authors, they have different models as they are listed in the table. Some are using short-term memory, and exponential hot winters smoothing. Then some are using neural networks and others random forests, as you can see in the table. So this is really current research papers in the year 2024. So, and in the table we also have some contributions that these researchers also did, and that is implementing what the topics is talking about. Then they also faced some limitations, which included missing data, overfitting, the dependence on historical data, then the quality of the data, computational complexities, among very many, as you can see, they are listed in the table. So with a problem statement, so our domain application problem is about fraudulent activities. Fraudulent activities. These include meter tampering, energy theft, illegal connections. So this leads to financial losses to these companies that provide these services. So we also realize that traditional fraud detection mechanisms or techniques, they struggle with these imbalanced data sets, because as we're working, we also realize that the data sets have very many non-fraudulent cases than the fraudulent cases, the fraud cases. So the goal is to develop an intelligent detection system that minimizes these false negatives that we see, and also work with the imbalanced data but maintaining the high precision. So some of the computation problems we realized were high data imbalances, because as I said, there are many non-fraud cases than fraud cases in the data set. So that data is really so imbalanced. So we had to incorporate mechanisms to see that we can balance the data to be able to work with it, such that the model we build is not giving false results because it's biased. So we also have temporal dependencies. So this is just basically depending on historical data to predict that, okay, the historical data influencing the current data. So that is also a computational problem, because sometimes if you're doing the model and it's a time series model, then okay, it involves dates, then that historical data may not really work well, and the model may not function very properly. So we also see scalability issues. So remember, we have to make a model that can be able to handle the increasing number of data, because these meters record large volumes of data day on day. So we have to create models that can really comply with that. So also the sparse and not noisy data. So the same as we're having very many zero values, so that becomes a computational challenge. So some of the research questions and objectives we're having is that we are asking ourselves how multi-strategy sparse distillation, a model that we built using that, can improve the detection of fraud and gas. Then we also look at what techniques effectively address this imbalanced data that we're really working with. And then we also ask ourselves that how does this undersampling technique that we were able to employ help to improve the performance of these personalized models. So some of our research objectives is that we wanted to develop a multi-strategy personal distillation model that can improve detection of fraud activities. Of course, maintaining the accuracy and the precision. So we wanted to also implement and evaluate the techniques that can handle these imbalanced data sets that we're working with, and also wanted to assess the computational efficiency of the proposed model compared to the traditional mechanisms that are used for fraud detection. So the research contributions are that we were able to develop a multi-strategy personal decision model to enhance fraud detection accuracy in gas and power consumption, but also keeping in mind the computational efficiency. So also implemented and evaluated some undersampling techniques to address the imbalanced data, and then we also assessed the computational efficiency of this knowledge sparse model to the traditional mechanisms. So the methodology that we worked with is that we had raw data. So this data, in the data set, we performed an EDA on it. So under the EDA, we're able to do some pre-processing and then also do some feature engineering so that we can obtain clean data that we can use to train the model. So when we obtain the clean data, we used it to first of all primarily train the models to evaluate and be able to choose which are the best model that we can use for our project. So when we trained the models and we got the results, and after evaluating the results, we did the model selection. We selected the XGBoost model, the artificial neural network, and the random forest models to act as our teacher models, and then we did secondary training on these data that the models that we selected, and we incorporated knowledge distillation to a student random forest So we're able to also obtain results, and like my friend is going to explain them, and then evaluate the results. So after evaluating the results and see that the model is complying with what we are looking for, so we're able to deploy the model. And under deploying the model, we did develop an AI, and sorry, we developed an API and an app that could be used. So we created an interface someone could interact with to detect whether a certain consumption is fraud or not fraud. So my friend would.
Hello, my name is Namita Haula. Let me start from where my friend stopped. Studying the data set description and exploratory data analysis. And so our data set was got from Zindi. It was collected by a company in Tunisian called Steg. And it has majorly two CSV files. One is the client information and one is the invoice information. So for the client information, it basically has the information about the client, where it says the region and the client ID and the district. And the invoice information basically has information on the transactions of the client. And then also has the meter information, the counter number, status, and counter coefficients, and all that stuff. And then it also has a target variable, which indicates whether a given client and their transactions are either fraudulent or non-fraudulent. It is either a 0 or a 1. A 0 represents the normal transactions, and then a 1 represents the fraudulent transactions. And then from there, we went on to perform an exploratory data analysis on the data set. And so in this bar graph, we have a region-wise, a district-wise distribution of clients. On the X, we have the districts and the clients in each district. Then this is a region-wise distribution of clients. And then here we have, so this bar graph shows the fraud target distribution. So 0 indicates the normal clients, those who are not involved in the frauds. And here 1, it represents the number of people involved in the cloud. So here we see that our data set is highly imbalanced. We have very many normal cases and very few fraudulent cases. And this is a very common case with cyber data or security data. We always have a few cases of the anomalies and very few, we always have a few cases of the anomalies, the frauds, and all, and very many cases of normal consumption or normal use. But regardless, we work with the data, and this is a bar graph showing the average consumption by tariff, a line graph showing the number of fraud cases in different months for the two counter types, which are gas and electricity, and the correlation heat map for the different features in the data set. And so from the exploratory data analysis and the collection of the data, we went and moved on to the modeling. So we trained a total of 10 models, which are listed here: the random forest, the logistic regression, the FVM, gradient boosting, and the neural networks, the autoencoders, the KNN, and the isolation forest. So after training these models, before I take you through the individual performance of the models, here I wanted to just talk about the method used to evaluate these models. So the performance of the models was evaluated based on the accuracy, the precision, the recall, and the F1 score. So since this was cyber data, we paid much more attention to the precision because it is very crucial. And what do I mean by precision? So precision is just is majorly a measure of the accuracy of the positive prediction. So of all positive instances we have, or of all instances that have been predicted as positive, how many are actually positive? So if our model makes a prediction if our model, like of all the fraudulent predictions it has made, how many were actually frauds? Of all the non-frauds, how many were actually non-fraud? And the recall stands for of all the total fraud cases we have, how many have been predicted? Of all the total non-fraud cases we have, how many were predicted? That is recall, and F1 score balances both the accuracy, both the precision and the recall. So here I just have a table that summarizes the performance of all the models based on this table. I first put in the accuracy and the precision for both classes, but then I also have tables ahead that I'll be showing you that have the recall and the F1 scores and all the rest. So for here, in this table, I can just make a general observation that the accuracy of the models some models it was really bad, and others it was promising, and other models it was really good. And all the models generally had a higher precision for the class 0, and all models generally had a low precision for the class 1. So this is the models were really biased towards the minority class, like they were biased towards the minority class, and they weren't performing well on it. And so this was because of the high class imbalance. And so when we noticed that, we realized we had to like do more pre-processing before. After exploratory data analysis, we had done SMOT because we had noticed that our data set was highly imbalanced. But then from the performance of the models, we realized we needed to do more advanced class balancing techniques. So we went on to do data augmentation, borderline SMOT, class weighting, and cost-sensitive learning to sort of like improve the performance of the models we had. So when we did that, then we came up, then we tried an ensemble method, or I could just rather call it a multi-threaded knowledge distillation approach. Then we trained 3 teacher models, and we did the knowledge distillation into the student model, and the prediction of the student model is what we have here, the model I call the multi-strategy model. And so here in this model, the accuracy was actually the worst we had so far, and the precision it was 89 for class 0. Then for class 1 it was 8%. This was still bad. And then and so we continued with fine-tuning the models we had. And so just a moment. So we went on to like fine-tune and optimize the models we had. So for artificial neural networks and the XGBoost and the for artificial neural networks and XGBoost, with the learning rates were tuned to balance the convergence speed and the performance, and higher rates, and we enabled faster training. Then for the random forest, we fine-tuned the parameters like the N estimators, the maximum depth, the minimum samples, and these were tuned to control overfitting and improve the generalization. And the XGBoost still, we went on to optimize the parameters, and then for artificial neural networks, a number of hidden layers and neurons and activation functions were adjusted to improve the accuracy and prevent overfitting. So after all this, and after all the fine-tuning, the best model we had on board was the random forest. It was the best model. So anyway, before I come to the random forest, so this classification report is on the model that is on the student model, where we did knowledge distillation, where we trained 3 teacher models, the XGBoost, the artificial neural networks, and the random forest. But still, the student model we had was overfitting, so this was still not fine. So, but after the fine tuning, the best model we had was the random forest, and it was not that general. It was the best model we had so far, and So anyway, as I was, so this year just generally talks about how I was saying how we went on to go to pick the random forest as the best model we had. So after fine tuning and applying the pre-processing steps to balance the data set and all, we came up with this tuned random forest that had an accuracy of 70, a precision for class 0 it was 70, and precision for class 1 it was 71, plus recall for class 1 was 72, recall for class 0 was 72, class 1 was 69, the F1 score was 71 and 70 for the different classes. And so far this model had a balanced precision. It is not necessarily the best, but from what we were doing so far, it was the best we had in the shortest possible time, because running these notebooks was actually taking a lot of time. It was time consuming as we are trying out this, trying out that, and as we're reading a lot of literature on how people have handled like highly imbalanced data sets and all that. So for us to continue like preprocessing and normalizing our data set, so this was the best model we came up in the shortest possible time, and we hosted it locally. So this is we hosted it via Flask, and this is the HTML file that renders it. And when you enter results here, it can make a prediction, and I'm impressed. And so far so good. It is promising, and we shall obviously continue optimizing it so that we have the very, very best we can have. And some of the conclusions and some of the conclusions and the limitations. So the best model, as I was saying, is that tuned random forest with the balanced accuracy of 70 and a balanced precision of, it was still around 70, and balanced F1 scores for both the classes of fraud and non-fraudulent classes. And then the other models like the XGIBOS, the attrition neural networks, and the autoencoder, they had a higher accuracy than it, but then a higher accuracy of 80 and 90, as I stated, but then they struggled with fraud detection, showing they were really biased on the majority class. Like they were performing so well on the classes for no fraud and performing so bad on the class that had on the fraud levels. So we couldn't continue working with those models. And some of the limitations we had, as I was talking about, the model performance trade-offs, that is between the precision and recall, data quality and imbalance. That was, yeah, it was a hassle. Then the data set limitations and adaptability, since this data set was collected in a different country, like the model may struggle to be incorporated like in another country. We may require like retraining on another large and diverse data set. And then we also had a few technical challenges faced during deployment. So the major insights from this is that the random forest is really reliable for fraud detection. I can basically recommend this. It was a take home, and the hyperparameter tuning is really essential and crucial for optimizing the model performance. As beginners in machine learning, this was, yeah, it was also a take home. And then advanced techniques such as SMART, borderline SMART to be specific, and cost-sensitive learning are needed to address the issues of class imbalance. And for the future directions, we obviously want to keep on trying so many things to have the best model. And so we want to keep on exploring advanced resampling techniques and try more ensemble methods, try deep learning approaches and experiment with advanced architectures. Yes, obviously to solve the problem of the data set being limited. And we want to explore with larger and more diverse data sets, obviously to have the best models. And so some of the contributions of our project is that we evaluated machine learning on an imbalanced data set. We emphasized model selection and hyperparameter tuning to solve the problem of class imbalance. We demonstrated the effectiveness of the random forest model for real-world fraud detection, and we aimed to develop a robust, reliable fraud detection system benefiting industries and customers. So the acknowledgements, we would really love to thank ourselves for the continuous research and not giving up. And also we want to thank our lecturer and supervisor for guiding us and the continuous support. Thank you so much.